So let's continue. So I was talking about news today and how we can apply game theory to it. There is a very simple game called Chicken. So classical setup of Chicken is as follows. There are two drivers and they drive towards each other and they can collide if they don't swerve. And so if they both go straight, they will collide and probably die in the crash. But if one of them swerve, then both of them survive. But the one who swerve, who made a turn, is considered to be a coward. So it's basically who is a brave person game about who is a brave person and who is a chicken that is coward. So if we make a matrix for this game, we can see two strategies available for both players. It's swerve or go straight. And if both of them go straight, this is the worst that can happen with both of them. If both of them swerve, it's like both of them are cowards, but it's okay then. So it's not that bad. The worst possible well, not the worst. The worst is the crash. But outside of crash, the worst that can happen with the player is if he's basically chicken. So he swerve, his opponent goes straight. So opponent is a winner, and the person who swerve is the chicken covered. So this story is about two crazy drivers, but interestingly, we can apply it to so-called brinkmanship. I have a link here. It leads to Wikipedia page. So if you have time, you can read it. Then you will have lecture slides. So basically, it's a story about two countries playing very dangerous game, trying to obtain something they want to obtain. And there are two strategies available to them. Here they are formulated like give in and stand firm, or you can call it de-escalate or escalate. And it's basically the same story, the same payoff structure. So there are four possible outcomes for every player. The best that can happen is win. It happens then you straight firm and your opponent gives in. The second best is compromise. Then both of you de-escalate, both of you give in. The next is lose. Then you give in and your opponent stand firm. And the worst is this outcome. I mean, in this context, you can think about it as a war, like full-scale war. So interestingly, you can apply the instrument we learned. You can think, what is Pareto optimal outcome in this game? What is prediction based on solution concepts we learned so far? So takeaways from this short story, game theory is everywhere. The game models can be productively used outside original setup. I hope you understand it. So we tell you stories about, in Battle of Sexes, we tell you story about one couple. In Chicken, we tell you story about two crazy drivers. In Prisoner's Dilemma, we tell you story about two criminals, but these models can be productively used outside of original context and original setup. You can think about them as the fables. So do you know the fable about crow and fox, for example? So they are not stories about animals, right? They are stories about how people can behave. It's just we tell it in this form, but it's something different actually. And the final takeaway can be that the exact numbers in payoffs are not that important. So you can ask something like, why we have these particular numbers, for example, 2 here, 3 here, why? It's just to make your life a bit easier, because it's easier to understand than we have just simple numbers. But what is really important is ranking of outcomes, as we done it here. So if ranking is the same, then it's the same game. So you can use different numbers, but if we have this ranking, it would be chicken game. And you can tell it in a different setups. So we use 2 different setups: original view drivers and about 2 countries, brinkmanship or escalation game. Okay, so to today's topic, Nash Equilibrium. Probably some of you watched, and almost all of you heard about famous movie called Brilliant Minds. It's the story of his life. He had how to pronounce it, schizophrenia. It's a very difficult word to pronounce. And he was a mathematician who got Nobel Prize in economics. So you can see that economists are pretty nice people. They give their awards to Kahneman, for example, was a psychologist. Nash was a mathematician, and they get their Nobel Prizes in economics. So why we need one more solution concept? So why we need one more solution concept? Why we can't just use dominance and be fine? The main problem is that there are many games that cannot be solved by dominance. There are many games that cannot be solved by dominance, and one of them is the Battle of Sexes, the game we discussed last week. Let me remind you about the setup. There is a couple. They love each other and would like to meet, but they have different tastes. Husband would love to see a boxing match. This is F, fight. And wife would prefer to see ballet, but they would love to meet each other. So they have some utility for meeting, and they get additional utility for seeing what they want to see. That is, the best outcome for husband is to meet his wife, but to see a fight, boxing match. Then he'll get free. And in a similar way, the best that can happen with wife is to meet his husband, but to see a ballet. Right? If they do not meet each other, so husband go to boxing match, wife go to the ballet. So they enjoy the show, but they still are not really happy because they do not meet. And the most funniest outcome is this one. Then they do not meet each other and watch the show they don't want to watch. So husband go to the ballet and wife go to boxing match. So let's use dominance approach. Let's start from the wife. Can we say that one of the strategies is dominant and another one is dominated? What do you think?
Not really. In the left outcome, the first strategy wins, while in the second outcome, the second wins.
I would use a bit different language. Let's say if husband plays F, he chooses to go to the boxing match, then the best strategy for wife is to go to the boxing match, to use F. If husband chooses ballet, then the best strategy for wife is to go for the ballet. So there is no dominant strategy. And because this game is symmetric, it's the same story for the husband. So there is no dominant strategy and there is no dominated strategy. So we cannot really solve it by dominance. So if you want to predict what will happen, we cannot if you use just dominance. What about safe strategy approach? We had a discussion that it's contradict the idea of rationality if we apply it to non-zero sum game, because if we, well, what is rationality for us? Rationality is players try to maximize their payoff. So safe strategy does not maximize payoff for a player if it's not zero sum game. But what about zero sum games? So can we use it? The problem with safe strategies, it is called minimax in this particular settings, and we're talking about zero sum game. This outcome sometimes is not consistent with expected one. For example, safe strategy here is 1, I mean to play U, and safe strategy for player 2 is to play C, right? So let me remind you how we do it. It's basically what is the worst thing that can happen. So this is a minimum. So what is the worst thing that can happen with player 1? If he play U, it is 1. If he play M, this is -3. And if he play D, the worst that can happen is -3. And now we choose the best out of worst. So this is 1. So if player 1 plays U, then he can guarantee that he will get 1, at least 1. And it's a reasonable strategy because in zero sum game you can expect your opponent to harm you as much as possible. So you want to choose the safest option. So we use the similar logic for player 2. Like the worst that can happen if he play L is -5. The worst that can happen if he plays C, it's -4. And the worst that can happen with him if he play R is -5. And again, we choose the best out of the worst, it's -4. So solution in safe strategies is U for player 1 and C for player 2. And seems like it should be 2 and -2, but the problem is we have these numbers. So we have kind of contradiction here, right? Next week, we discuss it and call it saddle point. So saddle point is then maximin equals minimax. So so these numbers are equal to each other, and then we can say we have a saddle point, and this is a solution in safe strategies that is stable, but here it's not. So we have some problems, right? Good story is, good news is that strict dominance is consistent. So what is consistent? Well, look, let's say we predicted that players will play U and C, so this outcome will be realized. But let's think about player 1. Let's say we are here. Should player 1 deviate? Well, yes, he should or she should deviate. He'll get 4 if he'll play D. So this is not stable. Player 1 will deviate and play D. And also player 2 will deviate and play L because -1 is better than -2. So this solution, it's not stable. We cannot expect it to be stable in the game. If you look at the solution by strict dominance, so let me start from the setup. So 2 lobbyists can act for their own party and get extra advantage +1, or push for the other party, and then the second party get extra advantage of +2. So basically, you can give 2 points to another player, and you can get only 1 player for yourself. And ideally, you would like you help party 1 help party 2, and party 2 help party 1, and then they both get 2. That's the best outcome. the best outcome. Or they can behave in a selfish way, then both of them get 1. And there is a variant then one party acts altruistically. So here party 2 helps party 1 and gives him 2, but party 1 plays selfish strategy and gets +1, so it's 3 and 0. And in a similar way here, it's symmetric. I hope you can see that this is basically prisoner's dilemma. This is prisoner's dilemma. I hope you can see it. And prediction by safe strategy. So let's, by the way, we haven't analyzed prisoner's dilemma last week. We haven't enough time. It was in slides, but we haven't discussed it. So maybe we should discuss it here. So what about party 1? Do we have a dominant strategy? Well, look, if player 2 plays selfish strategy, then for party 1 it's better to play selfish because 1 is better than 0. And if party 2 plays altruistic strategy, then it's better to play selfish, again, because 3 is better than 2. So selfish is the dominant strategy for party 1. And because game is symmetric, it's the same for party 2. So selfish is also dominant strategy for player 2. And that's why by dominance we predict that they will play selfish and selfish, and this outcome will be realized 1 and 1. And it's a bit tragic because it's not Pareto optimal, right? So can you show which outcome is Pareto optimal? What kind of Pareto improvement can we have from this outcome 1 and 1?
Well, there's the outcome where both parties take the altruistic strategy, and then the payoff of both of them increases by 1.
But what about this outcome 3 and 0? Can we say that it's Pareto optimal outcome?
Well, if we shift to 1 and 1 to 3 and 0, the payoff of party 1 increases, but the payoff of party 2 decreases, so it's not Pareto optimal.
No, it's not Pareto improvement. It's not Pareto improvement. But
oh yeah, sorry.
But it's a Pareto optimal outcome. I mean, to prove that, again, it's complicated, I understand, and some of you already had a seminar on it, some of you don't. But it's easy to prove that outcome is not Pareto optimal. You just need to find one outcome that is better for both players. And selfish, this outcome 1 and 1 is not Pareto optimal because 2 and 2 is better for both players. So this outcome that we predict will be realized is not Pareto optimal, and this is tragic part of it. But all 3 outcomes, 0, 3 and 0, 2 and 2, 0 and 3, all of them are Pareto optimal because you cannot improve welfare of both players, right? I hope you understand it. It's not that easy, so I hope you understand this idea.
Get it.
Okay, so based on strict dominance, we can predict that both players will play selfish strategy. So is it stable? Let's take a look. What about player 1? Does it make sense for him to deviate? So the logic here is we hold, well, in our thinking, we hold strategy of another player stable, like party 2 plays selfish. Does it make sense for party 1 to deviate? No, because he will get 0 and 1 is better than 0, so it's better to play selfish. Does it make sense for player 2 to deviate? Again, no, because if player 1 plays selfish, then player 2 can get only 0. So they kind of locked in it. They make their decisions independently, right? So if they, that's why it's called non-cooperative game theory, because they make their decisions independently. And for both of them, rational to play selfish. And paradoxically, it gives us a not Pareto optimal outcome. But what is the most important for us right now is that this outcome is consistent, it's stable, no one wants to deviate. There are no incentives for both players to deviate. They want both to stay here. They're kind of locked in this outcome. Definition of Nash equilibrium. So there is a game with players, actions, and payoffs. There is a profile, and some particular profile is considered to be Nash equilibrium if and only if any player has no incentives to deviate from his strategy, while other players follow their strategies. So in other words, no one wants to change his mind until the others don't do it. Do not do it, something strange. Okay, so now let's apply it to the battle of sexes. So let's apply this idea of Nash equilibrium to the battle of sexes. At the beginning of the lecture, we've discussed that there is no solution of battle the battle of sexes by dominance. There are no solution. There are no dominant or dominated strategies in it. What happens? So let's just use definition. Let's take a look at every cell and see if it makes sense to deviate for them. Let's start from this one. So you can see the answer already, but let's discuss. So let's start from wife. Does it make sense for her to deviate if husband plays F? No, because 1 is less than 2. So 2 is better. Doesn't make sense to deviate. What about husband? Does it make sense for him to play B? No, because 0 is worse than 3. So no incentives to deviate, and this is Nash equilibrium. What about this outcome? 0, 0. Well, you can see that wife can get free if she deviates, and husband can get free if he deviates. So this is not stable. What about this outcome? You can see that wife can get 2 if she deviates, and husband can get 2, right? If he changes his strategy from F to B, he will get 2. So it makes sense for him to deviate. And finally, what about this cell? So you can see that for wife, it doesn't make sense to deviate because she doesn't want to get 0 instead of 3. And for husband, it doesn't make sense to deviate because 2 is greater than 1, right? So we have 2 Nash equilibrium in this game. Does it intuitively right? Does it looks intuitively right? This is what you expect in this game or not? So what do you think? Can you hear me?
Intuitively, yes, I think.
So interestingly, there is no just one solution. So both situations are possible. And if we present later, we'll talk about dynamic games, and you'll see that in dynamics game, the order is very important. The person who makes the first step, for example, husband says, I will go to boxing match and I don't care, and then wife just have to go with him because it maximizes your outcome in this particular situation. But if they make their decision simultaneously, so there are two Nash equilibrium. So what happens here? What's the difference? Okay, I think something wrong here. Look, to prove that a profile is not Nash equilibrium is enough to find just one player who wants to change his or her choice. It's somewhat similar with Pareto optimality. It's very easy to prove that outcome is not Pareto optimal. You just need to find one outcome that is better for both players. In a similar way, to prove that profile is not Nash equilibrium, you just need to find one player who wants to deviate, who wants to change his strategy, and that's enough. Again, I want to bring you attention that solution is profile of strategies, and Nash equilibrium is not outcome. Nash equilibrium is not outcome. So if you say Nash equilibrium is too free, you are wrong, because Nash equilibrium is F for wife and F for husband. So Nash equilibrium is a profile of strategies. I hope you understand it. So how related to each other dominance and Nash equilibrium, these two approaches? First of all, you need to understand that they are different. They are not the same. Solution concept is a mathematical rule, how we can predict what will happen in the game. And these mathematical rules, they are very different, right? A week ago, we discussed dominance, we compared strategies, and now we just look at particular profiles and see if it makes sense to deviate from them or not. So these ideas are different. But even if these two approaches are different, they can give us similar predictions. And this is what happens with strict dominance. So solution in strict dominance is always Nash equilibrium. And if a game can be solved by strict dominance, then there is only one Nash equilibrium. So this is what you should remember. So if you can find dominant strategy in a game, you can just find Nash equilibrium using just dominance. But what about weak dominance? Okay, the next slide. In this game of two lobbyists, this is basically prisoner's dilemma, and you can see that there is only one Nash equilibrium. By dominance, we demonstrated that selfish and selfish are dominant strategy for both players. And you can see that there are no incentives to deviate for both players. For example, for player one, if player two plays selfish, then it doesn't make sense for player one to deviate and play altruistic, because he'll get 0 and now he has 1, and 1 is better than 0. In a similar way for player 2, it doesn't make sense to deviate because he'll get 0 instead of 1. So this is a Nash equilibrium. And you can check if other outcomes on the Nash equilibrium or not. For example, this one, 2-2, that is better in terms of Pareto optimality than 1 and 1. But the profile that gives this outcome, altruistic, this is not Nash equilibrium, because there are incentives for both players to deviate. So look, if player 2 plays altruistic, then it makes sense for player 1 to play selfish and get free instead of 2. And if player 1 plays altruistic, it makes sense for player 2 to deviate to get free against instead of 2, also to play selfish. So they basically, if you start game here, they both want to jump here and get free, but they both end here in 1 and 1. So this is what happens. One of them jump here, one of them jump here, and they both ends locked in this not Pareto optimal outcome. So what about weak dominance? It's problematic because we can lose Pareto, we can lose Nash equilibrium if we use weak dominance. So this is the story about two companies. One of them is incumbent, so it is for long period in these markets and has some market power. And there is new firm that is Entrant. Entrant has more efficient technology, so it can get something from these markets even without harming firm 2. Well, let's take a look at the payoffs. So for new firm, there are two strategies: don't enter the markets and enter the markets. For incumbent companies, there are two strategies, like aggressively push the firm out of markets, but this strategy has some costs, or just allow people to enter the market. So like the best what can happen with incumbent firm is new firm just decide not to enter the market. Then new firm gets 0 and old firm has 10. The second best are actually the similar. So if incumbent play aggressive and intimidates new firm, so new firm is deterred and decide not to enter, then new firm gets 0, but old firm get 5 because there are costs of this aggressive play. If new firm decides to enter and old firm plays aggressively, it gets 5 again because there are costs of playing aggressively, but new firm is just moved out of the market, so it gets 0. And finally, this is outcome then. Old firm allows new firm to enter the markets, and there are some costs for old firm, so it's 5 instead of 10. And there are big gains for new firm, it's 15. A bit complicated because it's not symmetric. So let's try to find dominant or dominated strategy. So can you find dominant or dominated strategy? What about for new firm? Do we have a dominant or dominated strategy?
We have a weakly dominated strategy.
Yeah, so enter weakly dominates don't enter, right?
Mm-hmm.
Because for aggressive, it's the same, 0 and 0. But if incumbent plays not aggressively, then 15 is better than 0. So we can predict that new firm will play enter. And then what should do incumbent?
Not to be aggressive. Yeah, because it's also a weakly dominant strategy.
Well, it's basically doesn't make sense what to do for incumbent, right? Because if new firms play enter, then basically the second firm chooses between 5 and 5. Okay, so this solution by dominance is enter and not, so this outcome. But if we apply Nash equilibrium approach, we can see that yes, this is Nash equilibrium because there are no incentives for both firms to deviate. For new firm, of course, it doesn't make sense to deviate because 15 is much better than 0. But for incumbent firm, it also doesn't make sense to deviate because it still get the same 5. So what's the point to deviate? Well, we assume that firms don't care about other firms' payoff. So they are not sadistic. They just, there is no goal to harm. Like firm 2 incumbent will not enjoy, but simply like reducing payoff of new firm. It cares only about 5. So 5 and 5, they are the same. So no incentives to deviate. So this is Nash equilibrium. But what about this outcome? Look, for new firm, it doesn't make sense to deviate because it's also 0. And for old firm, it also doesn't make sense to deviate because it's also 5. So this outcome is also Nash equilibrium, interestingly. So what happens if we solve, so main takeaway from this short story, if we solve the game with weak dominance, we can lose Nash equilibrium or equilibria, several of them. And this is problematic because these outcomes can be stable. So if for some reason firms find themselves in this outcome, playing these strategies, they will not deviate. They will be kind of locked there. So we predict that it can be stable. So this profile of strategies, aggressive and enter, it is also stable. So that's why we usually, you can use strict dominance without thinking, so just use it. But with the weak dominance, it's a bit problematic. So now we'll make several more examples. We'll practice finding Nash equilibrium or equilibria. So traveler's dilemma. The story is an airline loses 2 suitcases belonging to 2 different travelers. Weird assumption is that both suitcases, they are identical and their worth, their value is the same. That's a bit strange, but like it's the same. An airline manager tasked to settle the claims of both travelers explains that the airline is liable for a maximum of $100 per suitcase. So they have to declare the value of their suitcases, but they cannot declare more than 100 because company can pay only 100. To determine an honest value of the suitcases, the manager separates both travelers so they can confirm, similar to prisoner's dilemma, right? And ask them to write down the amount of their value, no less than $2, no larger than $100. He also tells them that if both write down the same number, he will treat that number as the true dollar value of both suitcases and reimburse, give them basically that amount. However, if they write down different numbers, then the one who writes down a smaller number will be paid this number plus $2, like a bonus, and the one who writes down bigger number will be punished for it, again by $2. So the important takeaway from this game should be that a game can have any number of equilibria, equilibria is a plural for equilibrium, right? So any number of equilibria, and in this game there are 4 of them. So there are 4 of them. So you can see that all the outcomes are Nash equilibrium. For example, let's start from this one. So for player 1, so he can rise his bet or lower his bet, right? He'll get 3. He'll get 1 if he rises, so it doesn't make sense to deviate. For player 2, he'll get 2 if he rises. No incentives to deviate. Here also player 2 can get 1, player 2 can get 3 if he deviates. No incentives to deviate. If in this profile of strategies, if player 2 plays D, he'll get 2. If player 2 plays R, he'll get 2. No incentives to deviate. And here is the same story. 2 instead of 2 and 3 instead of 3. So all 4 possible profiles are Nash equilibrium. Another story, maybe you played this game then you was in the kindergarten. Interestingly, this game was played ancient Greeks and Romans. So now we have smartphones and don't have to play these kind of games. So there are 2 players, so-called, we can call them even player and odd player. And there are 2 strategies. This is basically how many fingers can you show. It's somewhat similar to rock, paper, scissors. So you simultaneously show either 1 finger or 2 fingers. Very simple. And one of the players wins if the sum of fingers even. For example, both of them show 1 finger, then even player wins. An odd player loses. It's a 0-sum game. One wins, another loses. And if both of them show 2 fingers, then again, even player wins because it's even number. But if they have 3 fingers together, it's one of them shows 2 and another show 1. There are 2 possible combinations. Even player shows 1 and odd player shows 2, or even player shows 2 and odd player shows 1. So these are outcomes. Then they have 3 fingers, and odd player wins. You can try this game if you have a younger brother or sister, I think. So can you find Nash equilibrium here? So it's a very simple game, but it's a game without Nash equilibrium. Because look, if we let's start from this profile. So even player plays 1 and odd players plays 1. For even player, it doesn't make sense to deviate because 1 is better than -1. But for player 2, it's better to show 2 fingers, right? So odd player will deviate and show 2 fingers. So this outcome is not stable. Okay, so now we are here, but now it makes sense for even player to deviate. So we go here, but now it makes sense for odd player to deviate, and we go here. And now it makes sense for even player to deviate, and we go here. So we'll go in circles. None of the profiles is Nash equilibrium. None of them is stable. So the last example, is the cutting of the pie game. So there is a pie, and let's say you are the father of daughter and son, and they argue with each other a lot, and you want to teach them a lesson. And you basically tell them, so there is a pie and there are only 2 pieces in it. There are only pieces of the pie you can get. Now you need to write down how many pieces, and let's say it's a really tasty pie, so they want to have it as much as possible. And you need to write down how many pieces you want. But if I sum up these numbers, and if it's greater than 2, both of them will get 0. I'll just eat it myself. I also like this pie. So for daughter and son, there are 3 possible strategies. So you can ask for 0 piece, for 1 piece of pie, and for 2 pieces of pie, and in similar way for daughter. Of course, if both of them ask for 0, both of them will get 0. If one of them asks for 1 piece and another one for 0, then it's 1 and 0. If both of them ask for 1 pie, both of them will get 1 and 1 and eat the whole pie. The best possible outcome for every one of them is to ask for 2 pieces, but another one for some reason refuses, like 0 and 2, 2 and 0. And these 3 outcomes are outcomes then they want more than 2 pieces. So son chooses 2, daughter chooses 1, both get 0. Here it's symmetrical. Here daughter asks for 2 pieces, son asks for 1 piece, and both get 0. And finally, both of them ask for 2 and both get 0. So what do you think? Let's start from this profile 0 and 0. Is it Nash equilibrium?
No.
Can you prove that this is not Nash equilibrium?
Because son has incentives to deviate, because 0 is the least, the smallest number of pieces of pie he gets.
Yeah, so we expect that if we keep daughter's strategy fixed, she plays 0, then son will deviate and choose 2 pieces, right? So it's enough to prove that this is not a Nash equilibrium. What about this outcome? Again, it makes sense for some to deviate. What about this outcome? So what do you think?
It's best one for son, but daughter would like to deviate, definitely.
And to do what?
To increase your number, maybe. To not just receive 0.
She wants to increase her number, but she can only choose 1 of 3 strategy. So what strategy she will play instead of 0?
Under the condition that son plays 2 pieces.
So we keep his strategy fixed.
And this is an equilibrium.
Yeah, right. So this is Nash equilibrium. Interestingly, it seems like it's very unfair to the daughter, but it doesn't make sense for her to deviate because she can get only 0 and 0. So what's the point? So if son plays 2 pieces, then this is a Nash equilibrium. It's a symmetric game, so we can expect this one to be the same, right? So what about this outcome? 1 and 0. Is it Nash equilibrium?
No, because daughter can choose 2 pieces.
To deviate and get 2 points of utility instead of 1. What about this outcome? Is it Nash equilibrium? 1 and 1.
Yes.
Yeah, so we can see that there are no incentives for daughter to deviate because 1 is greater than 0 and 0, and there are no incentives to son to deviate. So it's a Nash equilibrium. So you can see that this outcome is not Nash equilibrium because son will deviate here and play one piece and get 1 instead of 0. This outcome, we discussed that this is actual Nash equilibrium because there is no incentives for daughter to deviate, 2 is greater than 1 and 0, and there are no incentives to son to deviate because he can get only zeros. And these outcomes, they are not Nash equilibrium, right? Because there are incentives for daughter to deviate here and for, well, wait. So what about this outcome? What about this profile? I mean, 2 pieces and 2 pieces.
It seems like they both don't have incentives to deviate because son will get all zeros, daughter will as well.
It's a bit funny, right? So it looks like the most stupid thing to do, to choose 2 pieces, but if they play it, they kind of locked in it.
I'm sorry, why?
I think I've done a mistake.
Because son can choose 2 pieces. This is the first row
Daughter
in
too.
this case. If the son chooses 2 pieces and the daughter chooses, well,
May I ask, can't they deviate to less amount of pieces? Maybe in the variant where both of them choose 2 pieces, they can deviate to 1 piece instead.
So, I mean, now they have 2 and to deviate to get 1? This is your question?
Yes.
No, because we assume that they want to maximize their payoff. And 2 is better than 1, so there is no meaning for them to choose 1 instead of 2.
Okay.
Okay, so we are talking about this outcome. Let's discuss daughter. So for daughter, it doesn't make sense to deviate because if she deviates to 1 piece, she'll get 0. If she deviates to 0 piece, she'll get 0. And for son, it's a similar situation. I don't know why I don't have. Yeah, I have. I just forget what I have on my slides. Right, so these 3 outcomes are Nash equilibria, and it's kind of evident, but this is a pretty funny outcome, right? Okay, so how to solve the game for Nash equilibrium? So far, we used a pretty straightforward way. We just relied on definition, right? So the definition is if neither player can increase her payoff by choosing an action different from her current one, this action profile is a Nash equilibrium. So basically, then we was discussing this game, we just apply the definition. Step by step, we apply the definition to every profile. So we discussed every profile, but it's a bit long, right? So if there are many profiles in the game, so let's say to every player 10 strategies available to him or her, then it will take a lot of time, right? Maybe there is a simpler way. Maybe there is a simpler way to, easier way to find Nash equilibrium. And this approach is called best response. So it's the second part of today's lecture. We started from Nash equilibrium and definition of Nash equilibrium, and now we'll talk about best response. So best response is the strategy or strategies which produces the most favorable outcome for a player, taking other player strategies as given. So we fix, in a similar way, we fix other player strategies. So we discuss simple games with just 2 players, So we usually say we keep other player strategies fixed, but it's completely possible to have a game with many players. So we keep strategies of all other players fixed, and best response is the strategy which produces the most favorable outcome for a player in a given situation. And action can be never best response if it's not optimal against any other player's actions. So a never best response action is not rationalable by definition. The danger here for you is to think that best response and dominant strategy are the same, but they are not the same, they're completely different. Look here. So let's first discuss dominant strategy, not best response. Let's discuss strategies of player one. So we compare A1, A2, A3, and A4. Can we find a strategy that is better than all others? For example, we have 10 here, great. We have 6 here, it's less than 7, so it's not dominant. We have 7 here, but 0 here. This is dominated by, this strategy is not dominant because if player B plays B1, then it's better to play A3. So we have no dominant strategy, right? So we compare strategy with another strategy, like the whole line. We compare the whole line, then we discuss dominance. So what about best response? I advise you to use the same notation that I use here. So look, best response of player A for the strategy B1 of player 2. So if player B plays B1, what's the best thing player 1 can do? He should play A3, right? Because 7 is the best he can get. So if player B plays B1, then the best response for player 1 is A3. So this is notation we should use. So best response of player A if player 2 plays B1, so its response for B1 is A3, right? If player 2 plays B2, what's the best response? The best response is A2. Please pay attention that best response is strategy. It's not number. So you can compare these numbers and typical mistakes students do, and you write down number as the best response. So if player B plays B2, then best response is 3. It's a mistake. It's not 3, it's A2. Best response is strategy. You respond with strategy, and then outcome is being realized, you get some payoff. The best response for B3 is A1, right? Because 7 is the highest number. And the best response for B4 is A4. So for every particular strategy of player B, we have particular best response of player 1. So now let's do the same thing for player B. So if player 1 plays A1, what is the best response of player B? So he chooses between B1, B2, B3, and B4. And B1 is the best response because B1 gives 7 instead of 5, 0, and 6. So B1 is the best response. So best response of player B if player 1 plays A1 is B1. Again, the best response for A2 is to play B2. The best response for A3 is to play B3. And the best response for A4 is, there are 2 best responses. So player B can play B1 and get 0, or he or she can play B3 and get 0. So there are two best responses. So you can see that B4 was never used, so it's never best response. And now if we combine, we've used some notation to indicate like best responses for player 1, and another notation to indicate best responses of player 2, and then we can find, then they basically they are best responses to each other, right? So here, if player 1 plays A2, then the best response for player B is to play B2. But if player 2 plays B2, then the best response for player 1 is to play A1. So this is a stable. Does it remind you something? So this is a Nash equilibrium. So sorry. It means that if best response of one strategy is another best response, then this is a Nash equilibrium. So it's a simpler way to find Nash equilibrium. We do not have to use definition, although we can use here. So let's check by definition if it's a Nash equilibrium or not. Let's start from player 1. Does it make sense to deviate for player A? He can get 2 if he plays A1, he can get 2 if he plays A3, and he can get 1 if he plays A4. All of them less than 3, so there are no incentives to deviate for player A. What about player B? He or she can get 2, 2, and 1. So all of them less than 3. So there are no incentives to deviate for player B. So this outcome is Nash equilibrium by definition. It's a pretty simple mechanics, like how to find it, but it's much easier if your notation is consistent. So I really ask you to use a consistent notation. Some students use pens with different colors, or you can use some symbols to indicate best responses for one player and best responses of another player. For example, here in table, I used a horizontal line for player 1, horizontal player, and vertical lines I used for vertical player. You can do the same, or you can use, let's say, stars for player 1 for horizontal player, and crosses for vertical player for player B here. So just use some consistent notation and then it will be easy. And let me repeat one more time that best response is strategy. Best response is strategy and not an outcome. So best response for A1 is B1, not 7. Not 7. Best response is strategy B1. And Nash equilibrium is best response, is profile of strategies. Nash equilibrium is, in this case, 2 strategies: strategy of player 1, A2, and strategy of player P, P2. So if you have to write down the whole answer, you should say, in Nash equilibrium, player 1 will play A2 and player 2 will play B2. And outcome would be 3-3. So player 1 will get 3 and player B will get 3. Of course, maybe you don't have to write down it's like the whole words, but you should understand this most important idea that Nash equilibrium is a profile of strategies and best response is strategy. Do you have any questions? Maybe you have questions about the first parts about definition of Nash equilibrium and finding by definition, or maybe you have questions about best response approach. Any questions? No questions. Chicken game is more like about 2 knights on a tournament. The one who doesn't fight is cowards. Well, maybe, yeah, you can apply the same game to many different setups, or you can think about it as a price war. So let's say there are two firms. You're too young to remember that in the beginning of 2000s, cellular companies like MTS, Tele2, or Megaphone, they competed for clients, and coverage was not universal in Russia, and it was a very vigorous price war. So company can cut prices for mobile network service. And this is basically chicken, because if another company also cut prices, both of them just lose, right? And the next firm can also, so it's again escalation, de-escalation game. So you can apply this model to many different situations. It's just maybe it's a more of a dynamic game. So when we'll talk about dynamic games, we can discuss how it's played in a dynamic setup. Okay, so you don't have questions? No oral questions? Can you hear me at all?
Yes.
Yes.
Great. So then, so let's apply this best response approach to the battle of sexes. So what is the best response of wife if husband plays F, that is boxing match? The best response is to choose F because 2 is greater than 1. So F is the best response for F. If husband plays ballet, then the best response of wife is to choose ballet. So it's here. So best response, so here. Best response of wife if husband plays ballet is to choose ballet. And now about husband. Best response of husband if wife plays boxing match is boxing match is F. Because 3 is better than 0, right? And best response of husband if wife chooses ballet is to choose ballet because 2 is better than 1, right? So we have 2. By using best responses, we can find 2 Nash equilibrium. So it works in the same way as if we just use definition. Okay, so it's all about best responses approach. And the last thing I wanted to show you is how we can apply Nash equilibrium in a continuous game. So what is a continuous game? It's a mathematical concept that extends the notion of a discrete game. In a discrete game, there are discrete strategies. For example, in tic-tac-toe, there are 3 strategies. In a battle of sexes, there are only 2 strategies. in, I don't know, here we have 4 strategies, and it's not very realistic, right? Because strategy can be continuous. So you think about a firm that chooses, let's say there is oligopoly, there are 2 summit plans, classical example of oligopoly, and they can choose the level of output. So how many salmon to produce, or oil companies, how much oil to produce, and it's continuous, right? It's not like a lot and not a lot. It's a continuous measure. So strategy can be continuous. Can we apply these best response ideas to a continuous game? So let's discuss the game 2/3 of the average. We'll give you prizes for winning in the next seminar. This game, guess 2/3 of the average. Let's simplify it, and let's say there are only 2 players. There are only 2 players. Each chooses a number from 0 to 100. So you play this game, you understand the rules, you perfectly understand what happens. But let's say there are only 2 players to simplify. So the goal is to be closer to 2/3 of the average. So can we find Nash equilibrium in this game? So let's say there is X and Y as a given profile. Then 2/3 of the average is 2/3 multiplied by 0.5 X plus Y. So it's average. It's a formula for average. So 2/3 of the average is 1/3 multiplied by X plus Y. The distance to the goal for the first player is X minus this expression, right? Does it make sense? It's absolute value, because you can be wrong in both sides, right? So this is the distance to the goal. And if we want to be as close to 2/3 of the average as possible, it means that we want to minimize, right, this distance. We want it to be 0. Then best response of the first player is X equals 2Y. So look, here best response is not a particular strategy. Like here best response for a husband playing F was F, just one strategy. It's a bit more complicated here. It's called best response function. It's a best response function. So best response of the first player is X equals 2Y. So for every value of Y, there is a best response. There is ideal X. Does it make sense if you think about it? Well, intuitively it makes sense. So no matter what your opponent does, if you know his number, you can choose such X that will give you exactly 2/3 of the average, right? Similarly, best response of the second one is Y star equals 2X. So there are 2 best response functions. And can you guess where is Nash equilibrium? How to find Nash equilibrium if you have 2 best response functions? Are you still here? Are you still alive?
Yeah. Yes.
So how to find Nash equilibrium if we found best response functions? What do you think?
To equate them?
Right, so it's completely the same logic as here. Nash equilibrium is then best response of one player is simultaneously best response of another player. So best response to best response. And here, if you set them equal, it basically means that best response of one player to the best response of another player. So they use best responses against each other. And of course, this is a stable situation because there are no incentives to deviate if it's already best response. For none of them, there is incentives to deviate. So x star equals 2y star equals 4x star. And it can be true only if they both equal 0, right? So then we discussed not so strict without algebra, but then we discussed this game. We've got this intuitively, we've got this idea that if players are rational, they play 0. And now we proved it. So we proved that if players are rational, they'll play 0. This is all I wanted to tell you today. Thank you for your attention. I'm ready to answer your questions. If some of you don't have questions, you can just leave. If you have questions, please ask. Questions?
Okay, I have a question. You said that basically here we don't care about payoff of our, I don't know, opponent, but in real life we usually care. And will we discuss situation when we care about payoffs of our opponents and how to deal with it?
Look, Bogdan, for example, this depends on how you formalize the game. So let's discuss Battle of Sexes. So we assume that they want to meet and that gets some utility from meeting each other. Is it the same as if they care about each other? I think it's basically the same. It's just it is already in the function of payoffs, right? So we just write down the function of payoff in such a way that if they meet each other, they've got more units of utility compared to the situation that they don't meet each other.
Here, yes, but I thought about it when we were discussing example of companies, when one company enters the market and another just allows it and receive.
Probably it's kind of, I don't where it is. Yeah, like you think this firm would hate this situation, then another firm has 15?
Yes, because it will give such great bonus.
I understand you perfectly. It intuitively makes perfect sense because if it's oligopolic markets, if one firm gets stronger, it means that another firm loses something, some opportunities, some access to capital, something. But we can write down it, then we formalize the game. We can just include it in payoff of this second firm. It's just very simplified game, right? In real life, of course, if one competitor became stronger in a particular market, another firm loses something. So it should be probably in a payoff. Although you can say sometimes if market is growing very fast, then they both can benefit from expansion, and it's possible that, well, it's not zero-sum game in this sense. I think it's a good question, actually. I think we should distinguish two things, like from methodological point of view, how we solve it, how we use mathematics. We apply, we assume that every player cares only about himself. But from substantial point of view, we can just include this thinking about another player into a function of payoffs for a player, and then it is there. So they can be not egoistic, actually. It's possible. Like, I think I've discussed it with Battle of Sexes. So yeah, not egoistic. They probably care about each other. Any other questions? Okay, so thank you for the class. Have a good day. You'll probably have some issues during the seminar, so just be active during the seminar, ask questions during the seminar. So bye. See you, some of you tomorrow.
Thank you for the lecture.
Bye.
See you.
Goodbye. Thank you.
Bye.
Bye.